exist, but they deal with other aspects of engineering now. Together with two partners, and I am one of the directors of Nova Fluid Mechanics. Since 2019, we have done 120 projects, and many of them are tall towers in Brazil. Hence why it's very important for me to be here today and talk about something that is very relevant to this country. So what do we do at Nova Fluid Mechanics? Very briefly, we mainly deal with wind loading on civil structures. So all the civil structures that are considered very flexible, that can be tall buildings, long span bridges, stadia. We also work on offshore structures and renewables. What I'm going to talk about today is, I'll talk about wind climate. I'll give you before a brief introduction of why we are doing this research project and how it happens. Wind climate, wind loading in general for tall buildings. And then I will go into specific of what happens to, how do we derive wind loads of tall buildings when we are in a thunderstorm-dominated region. And then I'll give you an overview of the research projects and what we want to do in the future. This is one of my favorite videos of a thunderstorm, which clearly highlights the complexity and the beauty of this wind phenomenon. What I'm hoping to achieve today is provide you with a few, not definitive answers, but a few things to think about and answer some of the questions. Such as, do we need to consider thunderstorms when we design a tall building? Do they make a difference? And if so, do we have a suitable, cost-effective, code-based methodology to do so? And most importantly, can we do better? I was very pleased to hear the other presentations today, both Sergio and Roberto, because indirectly or directly, they both mentioned that the codes, the standards that we use as engineers somehow are not necessarily suitable for the world of today, the world of today's engineering. And it's very important that in the commercial world, obviously not part of a university, we keep on asking ourselves the question, if can we do better, and try to work with university and the research centers to improve the ways that we have for designing structures. So, what is wind engineering? I would like to provide a definition simply because not all the civil structures or concrete structures need detailed wind engineering studies. One of my favorite definitions by one of the greatest wind engineers to me, Jack Cermak, is that wind engineering is best defined as the rational treatment of the interaction between wind in the atmospheric boundary layer and human beings and their work on the surface of Earth. But in the case of a civil project, how does wind engineering fit into the design and build of a civil structure? This is, you may recognize, it's a building in London, which was designed by a South American architect, Rafael Vignoli. I was involved in this project when I worked at BMT. And how do we go about, how does wind engineering fits in the process from getting to an architect sketch to a complete project? In this case, we worked extremely well. We were part of the team. What I feel is that for the majority of the buildings, wind engineering or the wind engineering specialist is not called to be part of the team soon enough. Andrea's presentation was really good and really interested, and he mentioned RWDI, who are doing the wind engineering for this extremely tall tower, because it's a 500 meters plus tower. But this doesn't happen, that the wind engineer is involved into the design at a very early stage, for instance, if we have 100 meters tall structures. And my personal and professional view is that this is somehow a mistake, because the involvement of a specialist could essentially save a lot of money to designers, ultimately to our clients, and we would be able to design better structures, because very small changes in the cross-section or the envelope of a building that would be very obvious for a wind engineers. Sometimes they are not taken on board, but they are not used by architects at early stages of the design. And more often than not, when we work as a company on tall building projects, we arrive at a stage where the envelope, the shape of the building is already defined and no changes can be made. So our service is simply to provide with the clients and the structural engineers with the loads, and nothing can be done to reduce or optimize the structures, which is a shame. But in some cases, when we have synergy, and I believe that the greatest projects come out of, result from the effort and the empathy and the synergy between all the people that are involved, in the various disciplines. So synergy between project managers, engineers, architects, and contractors is this key to successful projects. And engineering is driven by many aspects. We are all engineers, I'm sure, of all disciplines that are here today. Know very well the budget is always against us, and the schedule is always against us, and then we have all sorts of other technical issues that we need to worry about. But sometimes when we manage to collaborate with people that have that share with us the same goals, we manage to also achieve great things. And I would like to say that from the collaboration between Novacom Fluid Mechanics, which is my company, the University of Genoa, and engineer Sergio Stolovas, and also the client of a building, which I cannot mention now, led to a research project on the relevance of considering thunderstorm events when designing a tall building in mixed climate region, with the ultimate goal of designing wind-safer, more cost-effective and sustainable tall structures. Why did we collaborate with the University of Genoa? Obviously because I am from Genova and I studied there, but also because Genova, we were very lucky to already be working with Genova, because Genova is a center of excellence for the research projects on the thunderstorm events. There's the picture, if I can manage to work this. This is Giovanni Solari, was unfortunately passed away a couple of years ago. And he won a European grant to study specifically the effect of thunderstorm, and his ultimate goal was to be able to include thunderstorms or approaches to derive wind loading due to thunderstorm in the code. Unfortunately, he didn't manage to achieve this because he passed away, but his colleagues and the University of Genova are progressing the work, and they were of great help in this research project. Okay, wind climate is extremely important for tall buildings. There are several phenomena that we have to worry about as wind engineer. The majority of the towers are designed against synoptic events, which I'll talk about later, but obviously depending on where you are in the world, for instance, how do I go back? Yes. This map shows areas that are affected by typhoons and hurricanes, and you can see that Brazil is really safe. But obviously, if you are designing a tall building or a structures in these areas, the wind speeds will be much higher, and therefore the structure will be much more costly. There are other type of weather events. This is a thunderstorm, tornado, this is a shamal wind that occurs in the Middle East, that are somehow not considered less important. I mean, tornadoes, not really. There is a lot of research going on about tornadoes nowadays. But for instance, thunderstorms, we are not quite there. The research started very late in the day to me. They are somehow secondary weather phenomena, and therefore they are not codified very well, or in some cases not codified at all, which is a great problem for us as wind engineers and for structural engineers when we design structures, for instance, that are affected by tornadoes or these secondary, I wouldn't like to call them secondary, but I don't know how else to define them, weather events. So why wind climate is so important? This is a slide that I have shown many, many times. I should have added some the Brazilian, some of the Brazilian towns, but I haven't had the time to do so, but it's self-explanatory. On the x-axis, we have the design pressures, and on the y-axis, the height. And you can see that if you are designing a building in Kuala Lumpur, the design pressures will be more or less around 1 kilopascals. But you take the same building, you put it in Miami, that is significantly affected by hurricanes, and the wind pressures will be almost 3-4 times as much. So the structure will be completely different, more costly, and the engineers will have significantly more challenges. What does this mean? If you take two towns, I've picked Shanghai and Jeddah, the same building would have, in Shanghai, would have overturning moments at the base, which are key for the foundation and the superstructure design, which are 1.6 times those of Jeddah. Wind-induced accelerations at the top of the building will be almost twice as much. But I will now start talking about the weather events that are fundamental for Brazil. Obviously, there are the synoptic events, which are your standard winds, your standard daily winds. They are called extratropical depressions, and arises for difference in temperatures between the different areas of the surface of Earth. They can extend for thousands of kilometers, and they last for days. How do they look like when we measure a synoptic event? A synoptic event tends to be very stable. We call it a stationary event. You can see this is variation of wind speed measured by a standard anemometer with time, and in this space of 10 minutes, the wind speed is pretty much stable, 22.5 if I see very well, and the second graph shows you the wind direction. Wind tends to come always from the same wind direction. These events can be measured very easily with the standard anemometers that are not particularly expensive. And we do know, we have characterized as engineers these events very well. The formula that you can find in the code to extrapolate wind speeds at 10 meters, which is generally what the code provides up to the top of your towers, are very accurate formula. And we know that because we compare them with the full-scale measurements. Thunderstorms. Thunderstorms are very special and very complex events. This is what a thunderstorm drawing, if we wanted to draw a thunderstorm, what it looks like is a jet of air that goes from the clouds and hits the ground, and before hitting the ground, moves radially. And the wind speeds in these areas can be very high, extremely high. They can extend from 1 kilometer to a few kilometers or 10 kilometers. They can last minutes or a few hours. And immediately you can understand that this means that they are very difficult to characterize. They are all different. And different means that it's very challenging to find empirical formula that would allow us to codify the approach to derive wind loading for thunderstorm events on civil structures. Okay, this is an extreme case. It's a thunderstorm that travels extremely fast, and obviously the wind speeds will be very high, and you can see at the end the trees moving. So thunderstorms are very complex phenomena. Probably the most complex phenomena I had to deal with since the beginning of my career more than 20 years ago. Fujita, who is one of the scientists that studied the thunderstorms together with Giovanni Solari, defines the thunderstorms as a downdraft that impacts over Earth's surface and produces intense radial outflows and ring of vortices. Okay, compared to synoptic events, if you remember the previous graphs, you can see it looks very different. This is still variation of wind speed with time. It varies significantly. If we measure always at the same point. The wind speed varies significantly, and also the wind angle, the wind direction varies significantly. Can you measure accurately with a standard anemometer? No. It's very difficult. We can assess if the measurement is due to if we are measuring a thunderstorms or if we are measuring a synoptic event, in some cases, depending from the anemometer. But if we want to really characterize a thunderstorm, we need to have one of these anemometers. They are called LiDAR. They are very rare, extremely expensive. One of these would cost $500,000. So you immediately understand that all the university and the research centers that are now studying this phenomena need to have a lot of money to do so, because only the anemometer costs a lot of money. And it's not, I'm not an expert of this type of anemometers, but they don't work very well when it rains, which is a massive problem if you want to study a thunderstorm. Okay, press again. This is a CFD simulation of a thunderstorm. I've put a few pictures to highlight, because I'd like to answer the question, why are they so special? Because they are all very different. And thunderstorm is something that each one of us have experienced many times in life. And you know, sometimes I live by the sea and in an area where I can see you know, I'm not saying it's not thunderstorm dominated, but we have a lot of thunderstorms, and every time there is a thunderstorm, it always looks different. In the last 1 year, at least I've been looking at thunderstorms with a completely different eye, and I find it very, very challenging to think that one day or soon we will have a solution on the treatment of the wind loading on for thunderstorm events. What is the difference? Now, anybody that is a bit familiar with wind engineering would know that for synoptic events, your standard events, but even for typhoons or hurricanes, you increase the height. Oops. This graph, okay, this is height and wind speed. You increase the height above the ground and your wind speed increases. This is not true for thunderstorms. Thunderstorms, the wind speed increases up to a point, which is the point of the vortex. Point out, where you start having the vortex, and then it decreases again. This height, mysterious, nobody really knows. There are a lot of formulae that are based on measurements, but our research, and I'll explain it later, has concluded that we still don't know exactly where this point is. It depends on too many parameters. Now, are they important and for civil structures? We know that this graph shows variation of wind speed on the x-axis. Y-axis, you have a variation of height. And the blue profile is a wind profile of a synoptic event that grows with the height. And the red profile is a typical profile of wind speed for a thunderstorm event. And you can immediately see that small structures would be very susceptible to thunderstorm events. Very tall structures, like the one that the Andreas have shown, it's not for wind loading. It's not in the code. You won't find this information in the code. There isn't written that a thunderstorm event that you can avoid as a designer to look at thunderstorms for very tall or super tall or mega tall building. Actually, my view is that you need to worry about it, not necessarily for wind loading, but you would have to worry about it for cladding design. For the glazing, because the wind speeds could be higher than those for a synoptic event. For small structures, we know that they are a problem because these structures collapse, and they collapse due to thunderstorms. But what I'd like to focus today is on what happens when we have structures that are between 100 meters to 200 or 300 meters. Maybe 300, we are already out of the range, but the 200 meters. And these are the structures that are being built in Brazil at the moment. You know, many of the tall buildings in Balneário Camboriú, only a few are up to 300 meters, and the majority is below this height. So it's important that we understand this, because in Brazil, you have many areas that are dominated by thunderstorms. Now, these are disasters for which we have a record. I've put a few pictures that I have, but I have many, for small structures. So the ones that we know that can be very sensitive to thunderstorm events. One of them here is Brazil. Came to us as a problem, and a client called and asked if we could help in the investigation of the failure. It was very easy. There is a website that is a great website. If somebody is interested, I can give you the name that shows the lightning. So lightning is always associated to thunderstorm. The lightnings for almost any area in the world, variation of lightning with times. So we knew the time at which the structure collapsed, and I spent hours and hours looking at the lightnings in nearby, and eventually found that the collapse was due to thunderstorm. Why did it collapse? Because in the code there is not written very well how you can design for thunderstorm events. Our codes, and I mean all the codes that we have as structural engineer, focus only on synoptic events. Now, we don't have the same record for tall buildings. I haven't been able to find a record of a single tall building that failed or had significant damage due to a thunderstorm event. However, I have found records of glazing system and facade being damaged by thunderstorms. Now, are they relevant for Brazil? Every year, and this is a number that really amazes me, there are 60 million thunderstorms on Earth. And at any given time, so now there are other 2,000 thunderstorms that are occurring. These two graphs answer the question, are relevant for Brazil? Yes, this map shows that the lightning flashes per kilometer square per year. And you can see that in South America it's all very red, so many lightnings. Same here. And the number of thunderstorms per year, Brazil is significantly affected by thunderstorms. So they are important, and we need to consider in design, both for small structures and tall structures. Then I found this on the internet. I found that if you type thunderstorms Brazil or lightning, you find all sorts of articles. I like the title of this. I don't want to scare anybody, but it's a bit obvious from the information that I found that thunderstorm events are important. And we as engineers, structural engineers, or wind engineers, really need to try to address a better way to derive the wind loads and design for these events. As a company, we have done a lot of work in Brazil. This is the Brazil, the map of the wind speed taken from MBR, and I have highlighted in red the areas that I know are either dominated by thunderstorms or where the climate can be considered mixed, so that the synoptic events and thunderstorms are somehow equally important. How do I know that there are those red dots there? Because when we work on a tall building or another civil structures, obviously we use the code, but we also do a specialist wind climate study, and we take the data from several of the nearest airport to our site, and we do a statistical analysis from the data that were gathered from the anemometers. And via this statistical analysis, we are able to assess if the climate of a particular area is affected by thunderstorm events or not, and we derive site-specific design wind speeds. Very briefly, why is it important to do so? Because Brazil is a huge country, and this map is not very detailed. And therefore, there could be significant savings in the design of a tall building if you would have essentially a map that would be much more detailed. In the absence of it, we do that work. This is what it means when I say thunderstorm-dominated climate. All these graphs show return period. Normally for buildings, we use 50 years versus wind speed. You have three types of curves: synoptic, thunderstorm, and combined. Combined is what we design for. And you can see that in these three areas, which are all Brazil, the synoptic events, which are the orange line, have wind speeds for 50 years that are significantly lower. What does it mean? It means that if I could give you the answer that thunderstorm events are not important for tall buildings, now designers could take advantage of this and design for much lower wind speeds. And therefore buildings would be less expensive, less columns, more space for the occupants, so the advantages are infinite. Now, can we not as engineers simply design against thunderstorms? No, I said it already. Here there are several several codes. This is the Eurocode. Okay. Eurocode, American code, Brazilian code, some pretty pictures showing wind pressures on tall buildings. No, you don't find this answer of the code. They are barely mentioned. In some codes are not even mentioned at all, thunderstorm, as they weren't important. I'd like to say again, I mean, for tall buildings is debatable, but for small structures is a real problem. And that's why Giovanni Solari received so much money from the European community to do the research, because these structures were collapsing, small structures. Now, wind is important. This graph I particularly like shows the number of natural disasters on Earth. I'm sorry, it's not up to date, it's only up to 2005. But you can see the green lines are the wind storms, then you have earthquake, flooding, and others. Wind is very important. So when we design, we needed to pay a lot of attention on the wind engineering aspect. And not knowing how to treat thunderstorms, it means that its natural disasters could cause damages to our structures. So wind loading on tall buildings. Everybody else has already defined what a tall building is, but generally we are talking structures below 300 meters. These are some examples, obviously. How do we design them? We have, how do we assess the wind loads? We can start with codes of practice. Any structural engineer would not, as soon as they start a project, call the wind engineer. They would always assess or do some preliminary calculation with the codes. There are also design guides and handbooks, obviously boundary layer wind tunnel studies. I want it to be extremely politically correct, and I put numerical simulations, but I would never use a numerical simulation to assess the wind loading on a building. Not now. So the tool is that of wind tunnel testing. Why do we do wind tunnel testing? For several reasons. Obviously, the code is not applicable, and in most cases is written exactly in the code, is not applicable for structures that are above 100 meters because they are too flexible. But also, the code is not applicable when you have very complex shapes. The code is a set of rules, empirical formula that have been derived for simple shapes, squares, rectangular cross-sections, or triangular cross-sections, let's see, of circular cross-sections. But when you start having very complicated architectures, you cannot expect that the code would provide you with very precise wind loading. It's a problem for cost because you don't want to over-design, but also it would be a very approximate way of doing so, and cannot be done. The effect of the surround, that we test also to assess the effect of the surrounding buildings on our towers. And we do so for two reasons, because shielding is called shielding, so you have your tall tower and would be shielded by a lot of other towers. It's not always a shield. Sometimes buildings protect each other, but in some other cases there is the wind arrives, hits the first building, and then a lot of turbulence is generated, and the loading on your building might actually be worse. Very often we study buildings in the existing surround, so what's at the moment of the wind tunnel test is expected to be the surround, but also for the future surround, because we want to understand the impact of new developments. This is to show the complexity of the flow. This video, I really like. Again, it's still a very old video as well. And the shape is a rectangular shape, and it's flow visualization that we do in the tunnel with some sort of smoke. But you can see, in this area, how complex the flow is. And this is one of the reasons that CFD or numerical simulations don't work very well, or empirical methods that you could use, or calculations essentially, wouldn't work well either, because it's too complex. How do we measure wind loading on tall buildings? There are several methodologies, but this one is one of my favorite because in English we say kills two birds with one stone. It's a pressure, simultaneous pressures integration. You take a model, this is a probably 1 to 300 model of a tall building. It's generally 3D printed for maximum accuracy, and then it is instrumented with pressure sensors. Depending on the size of the building, it could go between 200 to even 1,000 pressure sensors for extremely tall buildings, or the mega tall. Each pressure sensor measures the pressures, and from pressure integration, we derive the overall wind loads applicable to the design of the foundation system, and the floor-by-floor loads applicable to the design of the superstructure. In terms of wind loading, which is the topic of